Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss capacitance of capacitor like parallel plate, spherical, cylindrical that are filled with dielectric. Let's begin. First, we have to calculate capacitance of a parallel plate capacitor with dielectric slab between the plates. We have to consider a parallel plate capacitor with each plate having the area A. Parallel plate capacitor one end taken as positive charge, other end negative charge. The area of each plate let capital A, and these are separated by a distance d. The separation in between these two plates is small d. Separation between the plates small d. Let the medium between the two plates is air or vacuum. At that of case, the capacitance of that parallel plate capacitor is given by medium in between the plates is air or vacuum. Then capacitance of parallel plate capacitor is given by C naught is equal to capacitance parallel plate capacitor with air or vacuum medium. It is A, area of each plate, epsilon naught, permittivity of free space divided by d, distance between the two plates. Suppose plus q charge and minus q charge is given to the plates of the capacitor that produces a electric field between the plates, and that electric field is E naught. That charges produce a electric field, that electric field is E naught. That from positive to negative, the direction of electric field from positive to negative. Let a dielectric slab of thickness small d is introduced between the plates. a dielectric slab that dielectric slab of thickness small t, and here small t is less than small d. Thickness of dielectric slab is less than the distance of separation between the plates. Since a dielectric slab is placed in between the parallel plate capacitor, then what happened? The process of polarization takes place. So, here that end negative charge developed, that end positive charge induced. In this way, an electric field is developed from positive to negative direction. That electric field be EP, electric field due to the process of polarization is developed in case of dielectric slab. So, the effective electric field, or we can say the net electric field inside the dielectric, here the effective electric field inside the dielectric, inside the dielectric is E is equal to, that is E naught minus EP. E naught minus EP, the net electric field inside that of dielectric. Now, the electric field between the plates over a distance t is E. That electric field within that of distance t, and over the remaining portion means d minus t is the remaining portion. Here the electric field be E naught. So, in this portion electric field is E, and this portion and that portion electric field is E naught. Okay. That the electric field within the distance small t be E, and the electric field of remaining parts means d minus t, that portion and that portion have electric field E naught. Therefore, we have to calculate the potential difference between the plates of that of capacitor. Here potential difference, then potential difference between the plates of the capacitor is VB, the potential between the plates of the capacitor. Relation between potential and electric field, that is electric field is equal to potential by distance. So potential is equal to electric field into distance. So here the electric field due to that slab is E, distance t. So here the potential Et plus the potential in that of remaining portion, that is electric field E naught, distance d minus t, d minus t. Here we know that from dielectric constant, from dielectric constant K is equal to E naught by E. Therefore E is equal to E naught by K, or V is equal to, in place of E we write E naught by K, E naught T by K plus E naught D minus T. Taking E naught as common, V is equal to, taking E naught as common, inside that bracket T by K plus D minus T, or potential V is equal to E naught, that is D minus T plus T by K. Again, by taking the surface charge density of the plates of the capacitor, sigma be the surface charge density of plates of capacitor and that will be charge per unit area. Sigma is equal to charge, Q be the charge, Q amount of plus and minus Q amount of charge is supplemented here. So charge per area A. Therefore we know the relation between E naught and sigma as E naught is equal to sigma divided by epsilon naught, the electric field intensity. These substitutions are put here, or we have V is equal to sigma divided by epsilon naught D minus T plus T by K, or V is equal to, in place of sigma we substitute Q by A. So Q divided by A into epsilon naught D minus T plus T by K. This is the potential between the two plates of the parallel plate capacitor. Now we can easily calculate the capacitance of a parallel plate capacitor with the dielectric slab between the plates. So hence capacitance of a parallel plate capacitor dielectric slab between the plates that is C, the capacitance that is charge per potential, or C is equal to charge divided by potential Q A epsilon naught d minus T plus T by K. Q cancel out. So, capacitance C is equal to A epsilon naught divided by, if we take d minus T as common, so d minus T as common inside that bracket, okay, d here T as common inside between these two terms, we have 1 minus 1 by K, okay. At the required expression for capacitance of a parallel plate capacitor with the dielectric slab between the plates, d minus T whole into 1 by K. Look here, a situation, if the dielectric slab fills with the space between the plates of the capacitor, means there will be no such dielectric slab. Or we can say there will be the total dielectric slab. Dielectric slab is fully placed in between the parallel plate capacitor. And what happened? A situation, if the dielectric slab wholly fills the space between the plates of capacitor. At that of case, C is equal to, in place of D is equal to T, C is equal to epsilon naught K A divided by small d. Here small d is equal to T. Dielectric slab is wholly filled. Or C is equal to K A into epsilon naught divided by D. A epsilon naught divided by D, that is the capacitance of a capacitor when there will be no such dielectric within that of medium, means the medium is air or vacuum. So, C is equal to K times of C naught. Therefore, we have C is greater than C naught. Here we take K is equal to, since K is greater than 1, Dielectric constant is greater than 1, so C is greater than C naught. The capacitance of a capacitor increases after we introducing a dielectric slab within that of plates. Here the capacitance of capacitor increases when dielectric slab is placed in between the capacitor. So, the capacitance of a capacitor is increasing when a dielectric slab is placed. Dielectric is placed. This is the required expression for capacitance of a capacitor that capacitor is a parallel plate capacitor when a dielectric slab is placed in between the parallel plate capacitor. Next, spherical one. Spherical capacitor. We have to calculate capacitance of spherical capacitor when a dielectric slab is placed. Capacitance of a spherical capacitor filled with dielectric. Let we consider a spherical capacitor that consisting of two metallic spheres, this one is a metallic sphere, that one with the another metallic sphere, here is the metallic sphere A having the radii small a, that one with the metallic sphere B having the radii small b, this metallic sphere of the radii small b, such that small b is greater than small a, and these two spheres, I just color it. Two spheres are separated from each other by air medium, that medium is air. If charge q is given to that of inner sphere plus q amount of charge is given to that of inner sphere A, the outer sphere B is earthed. So, an equal amount of negative charge is developed here within that of sphere B, as we earthed that outer sphere, is earthed. Now, these two spheres are treated as the spherical capacitor. The medium in between these two be air. Now consider a concentric shell of radius smaller. We take a concentric shell this is the concentric shell I picturize it. Of radius smaller and its thickness dr. Then the electric field intensity at a point R from the center O is given as the electric field intensity at a point, that point is at a distance r from the center O, is given by E is equal to 1 by 4 pi epsilon naught charge divided by distance q by r square, and the direction of that electric field is radially outward. Direction of electric field is radially outward. Now the potential difference between the spheres A and B is given as, let you take the potential at sphere A be V of A and potential at sphere B, let that will be V of B. Then the potential difference between these two spheres, the potential difference, therefore the potential difference between spheres A and B is given by, that is V of A minus V of B is the negative line integral E dot dr from B to A, Since E and dr are same direction, as we write E vector is parallel with dr vector, so angle between them 0 degree, cos 0 1. Therefore the equations are written as, from B to A, E dot dr, that is E dr 1 by 4 pi epsilon naught q by r square dr, as E dot dr is equal to E dr is equal to minus q divided by 4 pi epsilon naught integration from B to A dr divided by r square, 1 by r square minus 2 to the power 1, that is 1 by r, minus minus cancel out, that will be plus. So q by 4 pi epsilon naught and its integration 1 by r from limit B to A. Using upper limit and lower limit, we have q by 4 pi epsilon naught 1 by A minus 1 by B, that is the potential difference between two spherical cells VA minus VB. Taking the LCM here, VA minus VB is equal to q by 4 pi epsilon naught B minus A divided by AB. Now the capacitance of the air capacitor, therefore now we take that expression taking as medium between these two spherical metal be air. So the capacitance of the air capacitor C is equal to Q divided by potential difference VA minus VB. Putting the expression of VA minus VB, we have C is equal to Q cancel out. So 4 pi epsilon naught AB divided by B minus A. This is the capacitance when the medium be air between the two spherical metals. If the space between the spheres is completely filled with dielectric constant K. If the space between the two spheres is completely filled with a dielectric of dielectric constant K, then the value of electric field reduces to electric field E reduces to E by K. So the potential difference between the spheres A and B, therefore potential difference between the spheres A and B when these two spheres are filled with the dielectric having the dielectric constant K, that is VA minus VB is equal to Q by 4 pi epsilon naught into K B minus A divided by AB. Here we introduce the dielectric constant term K. Now therefore we can calculate capacitance of spherical capacitor filled with dielectric. Capacitance of spherical capacitor filled with dielectric is given by, that is C is equal to charge per potential VA minus VB. Putting that value, we have C is equal to 4 pi epsilon naught K AB divided by B minus A. That with the required expression of capacitance of spherical capacitor that filled with dielectric having the dielectric constant K. Look here, that term exactly how we get when we calculate relative permittivity. So relative permittivity R, or we can say K, with the permittivity of medium to permittivity of free space. Permittivity of medium let epsilon and permittivity of free space let epsilon naught. Therefore permittivity of medium epsilon is equal to epsilon naught into K, that is the permittivity of medium. Here in case of medium having the dielectric constant K, therefore in case of medium term we introduce epsilon naught into K. So, here we discuss how we can calculate capacitance of a spherical capacitor. That spherical capacitor is filled with the dielectric. First we take the expression taking air as the medium, this is the expression air as the medium, then taking the dielectric constant, and this is the final expression of capacitance of spherical capacitor filled with dielectric. Now, third one, in case of cylindrical capacitor, capacitance of a cylindrical capacitor filled with dielectric. Let we consider a cylindrical capacitor consisting of two coaxial cylinders two coaxial cylinders A and B, that is cylinder A, that is cylinder B, and cylinder A of radii small a and cylinder B of radii small b, and length of the cylinder, let you take the length of the cylinder be small l with the length of cylinder, length of cylinder be small l, and here B is greater than A, and let air is the medium between the cylinder A and cylinder B, air be the medium between them two, and we introduce a term lambda with a charge per unit length. Let we introduce a term lambda as charge per unit length. Let q amount of charge is supplemented to that of cylinder A, then ultimately same negative charge will be developed within that of cylinder B, and cylinder B is earthed. That is why the cylinder A and cylinder B are treated like the cylindrical capacitor. Okay. Let here we take a point P which is at a distance of small r from the axis of the capacitor, and that point P within the cylinders A and B. Then the magnitude of electric field intensity at point P, the magnitude of electric field intensity at point P is given by E is equal to 1 by 2 pi epsilon naught lambda by r, the electric field intensity at point P. That point P lie within the cylinder A and B at a distance of r from the axis of that cylinder, and the direction of that electric field is radially outward. Its direction is radially outward. Now we can easily calculate the potential difference between the cylinders A and B. Therefore, potential difference between the cylinder A and B is given by, that is VA minus VB is equal to negative line integral from B to A E dot dr. Again E dot dr, angle between E dr will be 0, as E vector is parallel with dr vector. Now putting the value of E here, so we have VA minus VB integration from B to A. Just put the value of E as E dot dr is equal to E dr 1 by 2 pi epsilon naught lambda by r dr. Okay. Minus lambda divided by 2 pi epsilon naught integration from B to A 1 by r dr. That integration will be ln r minus lambda 2 pi epsilon naught, its integration log r base E, limit from B to A. Now change the limit, the negative sign changes to positive one. Therefore, lambda by 2 pi epsilon naught log r base E, limit from A to B. Again using upper limit minus lower limit, that will be log B minus log A, that written as log of B by A of base E, as we take log B minus log A, that will be log B by A. That for potential difference between two cylindrical cells, that is VA minus VB. Now capacitance per unit length of the capacitor. Therefore, capacitance of unit length of the capacitor C is equal to lambda divided by potential difference VA minus VB, that is equal to 2 pi epsilon naught divided by log B by A of base E. Hence, the capacitance of a cylindrical capacitor of length L and the medium B air. Hence, capacitance of a cylindrical capacitor of length L with medium as air, that is C is equal to 2 pi epsilon naught into L divided by log B by A base E. Just we multiply the length of that of cylinder, that is the capacitance per unit length, that is the capacitance of that of total unit length, the capacitance of total length of that of cylinder, as you take L be the length of that of cylindrical capacitor. Now if a dielectric of dielectric constant K is filled between the space between that cylindrical capacitor, therefore what happened if a dielectric of dielectric constant K is filled between the space of the cylindrical capacitor So what happened? So the electric field reduces to if the electric field E, then it will be reduces to E by K, and the potential difference between the cylinder A and B, again the potential difference between A and B is VA minus VB is equal to lambda divided by 2 pi epsilon naught K log B by A base E. Here we calculate capacitance per unit length of the capacitor that filled with dielectric. Therefore, capacitance per unit length of capacitor filled with dielectric, that is C is equal to 2 pi epsilon naught into K divided by log B by A base E. This is the capacitance per unit length. Then the total capacitance, then the capacitance of cylindrical capacitor of length L, capacitance of cylindrical capacitor of length L with dielectric, that is C is equal to, just we multiply L here, that is 2 pi epsilon naught K L divided by log B by A base E. That is the required expression, 2 pi epsilon naught K L divided by log of B by A base E. Okay, this is the required expression as the capacitance of that cylindrical capacitor, and that cylindrical capacitor of length small l, and that filled with the dielectric. Then the capacitance result will be C is equal to 2 pi epsilon naught K into L divided by log of B by A base E. Just multiply L in that of expression. This is the required expression for cylindrical capacitor when a dielectric is placed in between them. First we take the expression by taking air as medium and taking the unit length, then taking dielectric in between them and finding that expression. So with the help of this video lecture we understand capacitance of capacitor like parallel plate, spherical and cylindrical, these are filled with dielectric. First parallel plate capacitor, first we take the expression taking air as medium, then putting the dielectric and find the expression, then compare with these two capacitors. Next for spherical capacitor, taking air as medium and calculating the capacitance, then filled that medium with dielectric and finding that capacitance. Last one, for cylindrical capacitor, same way, first take air as medium, finding the expression. First we take the capacitance for unit length, then capacitance of total length as medium as air, then same thing, that medium is filled with dielectric. First we calculate the potential difference, then for unit length, and finally for total length L, the capacitance is calculated. So, with this useful and informative notes, let me wind up this session. Thank you.